An example. I thought I had a white version of this, but anyway, I don't know where it is, but you've got a good version here in your copy there. So, but anyway, this is from the 50s through the 80s, how it improved, and basically you can see how, let's see, that's LCO, that's that diesel that you don't want. That's less than half of what it used to be back then. And let's see, well, that's the slurry, I'm sorry, the real heavy stuff. And the bad diesel is going down some, but see the gasoline, that's really increased thanks to improvements in catalyst. So, and then the next valuable product is C3s and 4s, which make alkylate, and that's increased significantly. And even the gas make is going down a little bit, so, and it's worth a lot less than these liquid products. So anyway, that's kind of an example of how it's improved with catalysts, and true of almost every refining process. Hydrocracking, hydrotreating, the catalysts are so much better and made for more profit and better fuels. So, okay, let's see here. Now, I think I had another. Let's see here. Maybe it's on this one here. Okay, that's the one I really wanted. Okay. In fact, I just did a rough calculation, as you can see, how much more gasoline you're making now and how much more alkylate, using some fairly typical margins for a 100,000 barrel cat cracker. The increased C3-4 and gasoline should be worth about $300,000 a day, or $85 million a year in 2006 dollars. So that's how much more profitable these units have become. They're making that's pretty big. So most of them aren't that big. Even Chevron's isn't that big. So, but anyway, say even less. Say another $50 million a year due to improvements in catalyst. So that's a reasonable amount of profit increase. So okay, back to where we were. Let's see this one. Okay, let's look at some of the products you make. See now, how did I do that? Here, or is that? Expand it. That one there? Oh. Oh, up? Wow. See now. Let's see if this will do it. Okay, that won't. So which icon do I push? Okay. Anyway, now one key thing in how good the products you make and how much is what kind of feed you have. And ideally, you'd like a paraffinic feedstock. It cracks much easier. Aromatics, paraffinic feedstocks are cracking down aromatics, so if they're already aromatics, they don't do much of anything except make heavy crap that you don't want. And there's an example of how much conversion will go up from a paraffinic feed to an aromatic feed. And gasoline makes much higher with paraffinic feed. And butylenes are much higher. There's the key one right there, the olefin. And then propylene, same thing, much higher with paraffinic feedstocks. So light cycle oil goes down. And a lot of refineries, it's hard to get rid of this. You almost need a hydrocracker to get rid of it. So, which is a very expensive unit. And this make of this decanted oil, it's called slurry oil, decanted oil, clarified oil, goes down tremendously. And there's not much you can do with this either. So, and also the swell went up considerably with a paraffinic feedstock. Keep in mind, these are, as I mentioned with hydrocracking, these are free barrels. You started with 100 barrels and you got 108.5. So that extra 8.5 or 14.5 barrels is worth the price of crude plus the improvement over crude. So that's a lot of dollars there with that swell. That's called swell. And swell is swell. All right, Coke make went down quite a bit, so that's pollutants out the regenerator stack, and less of those. And fuel gas, less fuel gas, which is really not all that valuable. I mean, you do burn it in your furnaces, but you know you want to make as little as possible actually. H2S went down significantly too. So anyway, you'd like your nice paraffinic feedstocks, but on the other hand, those feedstocks are cheaper. So like everything, there's a balance to make. You know, save money on the crude versus you don't convert as well. Okay, now what we got? Let's see here. Next one, product quality. Okay, not only do you make more of the good things with the paraffinic feedstock, but you make better quality. For instance, the sulfur in the gasoline range will be much lower, 100 versus 1,000. And right now they're really cranking down on the sulfur in gasoline. They're requiring like 15 ppm. And most of the sulfur in the gasoline comes from the cat cracker gasoline. So they're putting new units now to remove this down a lot lower than they used to. Like I say, you have to get to 15, so you can see that they'll put a special unit just on this gasoline, a SCC gasoline hydrotreater, just to get rid of that. Octane ratings. Okay, now actually, octane's a little lower to the paraffinic. Remember, aromatics make good octane, so you make a little better octane with these feeds. And so light cycle oil is a little better with the paraffinic feedstock, and sulfur much lower. And usually you try to blend this off in diesel, but they've also lowered that now down to 15 ppm. So it's pretty hard. It's pretty hard to get too much 5,000 ppm plus stuff in something that's going to be 15 ppm, as you might guess. So that continues to be a problem, getting rid of that in a refinery. And there's a lot of names for the bottom stream. Slurry oil, called slurry oil because it's full of catalyst. It is a slurry, literally, with solid and oil. And actually, sometimes they'll actually take this over to some kind of a solid separation unit, and now it's clarified oil. So a couple names for it, but anyway. So that gravity gets a little better too with your paraffinic feeds. -3. Now, anybody know what that means? I mean, significance of a minus number on API? Heavier than water. 0 is water. No, I'm sorry, 10 is water. So actually this is heavier also. So it's some scale they made up for gravity to expand the range of it. And water's 10, so that's the problem with this. See, it's a oil stream that doesn't even float on water. See, it's really hard to get rid of. So, and then of course super high sulfur level. Let's see now, 10,000 is 1%, so that's 2.5% sulfur there. Okay, let's see here. Let me go back to make sure I didn't have another one here. Let's see. Oh yeah, now here was some numbers that I came up with. What you're really interested in a petroleum unit that's making gasoline is, as we saw, you know, this made more barrels of gasoline, but this made a little better octane. What really matters is octane barrels, octane time barrels. So then for this paraffinic, so here's roughly multiplying these two together. Here's the octane barrels for an aromatic feed, roughly 5,000, and 6,300 for a naphthenic feed, which is intermediate between these two. 6,500 for paraffinic. So see, you made a whole lot more octane barrels, and that's really what it's all about. Kind of a summary there. Okay, now Where we go now? Okay. Okay, now here we'll go to Excel spreadsheet. Okay. All right, let's do this one first. Okay, now you got to decide what temperature to run in your reactor. And here's what happens with temperature. I guess I can't get that to expand, but you got a picture of it there. And well, anyway, there's kind of the temperature range you operate with it in a reactor. And so as you go up in temperature, then let's see, your cycle oil will stay about the same. Gasoline actually goes down a little bit, but what goes up is the olefins, which will make alkylate. And alkylate has higher octane than FCC gasoline. So, and let's see what else we got. Gas. You make more gas, of course, as you raise temperature. Not surprising. But actually, amazingly, you made a little less coke, which is a positive thing. So you have to decide what bed temperature to run, and so it'll be an economic decision. And here it is graphed up here. So, okay, we'll go back to this then. What's next here? Okay. Let's look at some of those others on that page too while we're at it. Okay, some other trends here with reactor temperature. The chemical types in your product. Now, on the gasoline, you want aromatics. So as you can see, as you raise temperature, you're going to make a lot more aromatics, which will make for high octane and better gasoline, and less paraffins, which you really don't want. Now, in a hydrocracker, you might want that because it would, or you might want more paraffins because it makes better diesel. But gasoline, you want the aromatics. So, and actually, the olefins help octane also. So, but finally, you'll get to a point if you go too far, you'll make more coke and start destroying that extra gasoline you made. So there's a limit, and that's probably at about 1,000 degrees. Okay, let's see what. And here it is up here plotted. So as you can see, basically the paraffins in the feed are converted to paraffins and naphthalene converted to olefins, and then to aromatics. Okay, let's see. Paraffins to olefins. That one's olefins, right? And then eventually to aromatics. And it's as you gradually drive hydrogen out, you get better and better octane typically. And as you raise temperature, then you'll, as it says, you'll have more. What's the blue in there? More aromatics and more olefins and less paraffin. So all that's leading to better gasoline. Okay, now that's the C5 and lighter portion is what has the olefins in it too. Now that'll go to alkylation. So as you raise temperature, you'll get more of these olefins, which will go to alkylate, and less of the paraffins. And most of the paraffins aren't worth that much. I mean, isobutane and isopentane are worth something, but most of them go to LPG and fuel gas, which are products, and you make some money on them, but not like what you make with alkylate. So that's another good trend that occurs when you raise temperature in the reactor. And it shows there, of course, the red being what you want. Okay, back to this one here. Okay. Okay, a little bit about what's going on in the FCC reactor. And once again, versus the type in the feed, is it paraffinic or is it... the paraffins in the feed, they're long chain, so you can guess that they, it's easy to hack up that straight chain. And say you have a C20 paraffin, it'll break it into smaller paraffins, maybe a bunch of C5s and C6 paraffins, and since it's smaller molecules, they need more hydrogen, so you'll make olefins, which are unsaturated, and that's where the octane comes in. So isoparaffins have better octane than normal paraffins, so pretty much rupture the same way. And now you get to the ring compounds, the naphthenes, and if we need to pull out that old chemistry stuff I had the last time I was here, we can do that, what a naphthene is and what an aromatic is. We can always do that here. But what happens in there is you'll open that ring. Sometimes you'll have all these rings fused together, a whole chicken wire, a bunch of rings, real heavy stuff, and it'll split these rings apart and make smaller aromatic rings, and then olefins and paraffins. Pure aromatics hardly crack, and we kind of saw that in those earlier slides where you didn't convert very well with aromatic feeds. Now you have aromatics with a alkyl group on it, a paraffin group coming off the side of one of the points. It'll take that typically take that paraffin group off the side and shear it off, and then you'll go down to the bare aromatic ring and make an olefin. And straight olefins, they're kind of like the paraffins, long chain, and they'll rupture similarly, just like those did. So anyway, there's some of the things that happen in cat cracking. Let's see. I guess there was one other thing. Now, I don't have this on a graph. Let's see. This one, look at the last graph in cat cracking. Hopefully everybody has it. The one here from Exxon, does everybody have that one? Okay, that's just an example of, it's off the internet, so I really couldn't put it on the computer. But it shows with this new process, resid cracking, where it fits in as far as resid conversion. And I guess you had coking, last week? Helmy gave coking, did he, or was that the week before? Okay. Anyway, so thermal processing, the one with the highest Conradson carbon, that's coking, basically, coking and vis breaking. And I think he probably got into that. And if you have heavy enough stuff with enough carbon in it, you'll have to go the thermal processing route, which is very non-selective and kind of brutal in nature. And you can put heavy hydrotreaters, but you can also take a cat cracker, just like I showed you, and add a second regenerator. If you're going to take a heavier feed, you got a lot more coke, you need a lot more air, and a lot more regenerator room in order to burn off this air and not get too hot. So you make a resid FCC by, that's the main thing you do, is add more regeneration capacity to burn more coke. And so that's one big improvement they made in FCCs, to handle a little heavier feed versus sending to a coker. A coker is just a big sledgehammer, and it doesn't make very good products, and so you don't want to send any more there than you have to. So that's a little trick to be able to send more of the heavy stuff to the cat cracker, and it does a better job converting to gasoline than the coker would. So just thought I'd throw that in the end of the cat cracker part. Any questions on cat cracking? We'll go on to some other stuff here. Figure it's break time, or yeah, let's do a break time. Good time to break anyway.